to in this video is talk about solids of revolution and then ultimately finding the volumes of solids of revolution. Now, to do the very first part of it that this video focuses on, I want you to recall that when you want to find the volume of a cylinder, you take the area of the base, then times the height. Now, if it's a right circular cylinder, that means the base is a circle, and as you pull the circle to the circle through space, you're making it so that the one of them's right on top of the other. So the cylinder's sitting upright with a 90-degree of the edges with the base. So the volume of a right circular cylinder is V is equal to pi r squared h. And that's just a volume from geometry. Now, as far as a solid of revolution goes, if I take, for example, this object and I place it so that it's on the x-axis, and let's just go ahead and trace around it. And I have this particular curve. And think about this as looking at the region that's caught in this curve. Now, I know this one's not a function, but it's just going to give a demonstration of what we're talking about. Now, in these solids of revolution, we need to say what axis it's spinning around for the revolution part. So for this particular example, I want it to spin around the x-axis. So I'll note that in my diagram by putting this little loop in there to give a person looking at that what they need to visualize. So think, if I took this region and I spun it around the x-axis, what would it make? Well, going back to, we traced around this figure, and think if I spun this around the axis, it would make that solid. So actually, this is just like a wedding decoration, it's just about. But, so that's the thing that you want to imagine as you're going through this. Here's another example. This would be if you took and traced around the outside edge and spun it around the x-axis. This would make a sphere. So hopefully that helps you kind of visualize what's going on with this, because that's going to be a key component of getting these problems set up correctly and ultimately finding the volume that they're requiring you to do. All right, so now if we have this region that's bounded on one side by the x-axis, and it's being revolved about the x-axis, so it's bounded on one side by the x-axis and it's being revolved around the x-axis, then when I take a cross-section of it, the solids are going to be very thin little cylinders. So if I just had these little subrectangles and I spun them around and around, those are just going to be cylinders. And that's why it was important for us to do the volume of a cylinder. Well, for these cylinders, remember, this is what the x-axis is what I'm spinning it around. So from the x-axis to the curve, that's going to be your function value. And that's going to be your radius. So for these that are tied along the x-axis and spun around the x-axis, I'm going to have my radius squared and then pi for the volume. What about the h part? Well, the h part is just this thickness of that little subrectangle that I spun around, and that's just your dx. So the formula for the volume of this region that's bounded on one side by the x-axis, being revolved around the x-axis with the cross-sections that are cylinders, is going to be the definite integral from a to b. So if this were my a and this were my b, and again, it would be where you would have it, we're going to take it just about to here, because as a demonstration, I need it where it's against the x-axis throughout, of pi times your radius r of x squared dx. And remember that pi is just a constant. So I can factor that pi out in front and get that the volume is equal to pi times the integral from a to b of r of x squared dx. So now let's look at an example. So let's say we want to find the volume of a solid obtained by revolving y equal x squared plus 1, x equal 1, x equal 3, and y equal 0 about the x-axis. So here I've drawn the parabola y equal x squared plus 1. X equal 1 is the vertical line at x equal 1. X equal 3 is the vertical line at x equal 3. Y equals 0 is the x-axis. So the region we're talking about is this enclosed region right here. So again, with these, just like when you're doing the areas of regions, it's really important that you graph this and visualize what's happening. Now I'm spinning it around the x-axis as per the description of the problem, and you see how the x-axis bounds the region throughout. So if I take cross sections that are vertical subrectangles through that and they're spun out around, that will give me my little cylinders. So this volume is pi times the integral from 1 to 3. Now my radius is from the x-axis up to the curve, so that's just the function output of this y equal x squared plus 1. So that's the radius squared, and it's dx because my subrectangles are tall and thin, they're going vertical. Now to go through and calculate this, we're going to multiply out the binomial, so that's x to the 4th plus 2x squared plus 1 dx. Integrate it, so it's pi times, add 1, it's letter base to number power, add 1 to the exponent and divide by that, so it's 1/5 x to the 5th plus, add 1, divide by that, 2/3 x cubed plus the antiderivative of 1 is x, evaluated from 1 to 3. So then you have pi, and you're going to plug in the 3 minus plug in the 1. So it's 1/5 times 3 to the 5th plus 2/3 times 3 cubed plus 3. Then minus, in parentheses, 1/5 times 1 to the power of 5 plus 2/3 times 1 cubed, and then plus 1. And when you go through and you do the calculations for this, it's pi times 1016 over 15. And remember, that's like pi over 1. So my volume is 1016 pi over 15 cubic units.